Hello, and welcome to this talk at the 12th Annual Non-Volatile Memory Workshop. My name is Jessica Sinters, and I'm a PhD student at Duke University. Other members of this research team consist of Xinyu, Ahmed, Hareedy, and Robert Calderbank. This talk covers our recent results on calculating the power spectral density of constrained codes that are typically associated with level-based signaling. I'd like to begin with a brief history on constrained codes. Shannon first introduced coding in constrained channels in 1948 and showed that a finite state transition diagram can be used to generate all of their sequences and calculate the channel's capacity. Then, in the 1980s, run-length limited codes began being used to improve peak detection in magnetic recording devices. These codes were associated with transition-based signaling. In modern days, constrained codes find application in various systems, such as certain magnetic recording systems that have adopted sequence detection, low-resolution media, flash memory, and communication systems. RLL codes used transition-based signaling schemes such as NRZI. In such a scheme, a bit 0 would correspond to no transition in the signal. A bit 1 would correspond to a transition. This can be seen in the top signal of the figure shown on this slide. Our research focuses on codes using level-based signaling, such as NRZ signaling. In this case, a bit 0 would correspond to the signal being at -1, and a bit 1 would correspond to the signal being at the level +1. This can also be seen in the figure below the NRZI signaling. The constrained codes that are associated with level-based signaling that we provide general results for in our papers are A-loco and loco codes in the finite length realm. I've gotten listed here two different sets of patterns that are going to be the forbidden patterns for A-loco and loco codes. These codes have two key parameters, X and M. X defines that forbidden set within AX and SX, and M is going to be the length of the codes for A-loco or loco. A-loco finds primary application in flash memory, where you want to avoid high, low, high charge levels on cells adjacent to each other, as where loco finds application in magnetic recording devices and communication over transmission lines. Providing closed-form solutions for a code's power spectral density is particularly useful for system designers as they consider what codes would work best for a particular application. For example, if an application requires a code to be DC-free, the power spectral density of a code can easily demonstrate whether that code fits the constraint. We provide a series of steps for calculating the power spectral density of any level-based code. First, we provide instruction on how to model a code in a finite state transition diagram, or FSTD for short, by creating a grid of states where the columns correspond to a bit position and the rows correspond to a specific pattern of previous bits. Using the FSTD, the OSTD can then be generated by labeling states that result from the previous bit being a 1. Throughout the previous two steps, it's important to keep track of transition probabilities so that the one-state transition matrix, G of D, can be calculated. The full formula for calculating G of D entries is provided here. We then adopt the following signaling scheme, where Xn is the code sequence, Yn is the modulated sequence, and W of T is the right signal. We assume rectangular pulse shaping. In steps 4 through 6, we provide equations for calculating either the intermediate or final right signal's power spectral density. Most often we are concerned with this power spectral density of W of T, but sometimes it is useful to know the power spectral density of the intermediate signals. Here is a quick example of calculating the power spectral density of an A-loco code. We use A-loco where M equals 4 and X equals 1. This code has the code book listed here on the left, and you can notice that in this code book, there is no pattern of 101 occurring. This is the FSTD for this code, and you can see that we've already labeled the OSTD states as F1, F2, F3, F4. Notice that we end up being able to combine states that have the same exiting paths and probabilities. That's why there are two labeled F1, two labeled F2, etc. This step followed the previous first step that we showed you, where we used the grid of states to determine this FSTD. Here we have the OSTM that is generated from the FSTD. Notice there are patterns in its entries. Once we noticed that, we found that we were able to generalize the OSTM for any ALOCO code via its parameters M, X, and the codebook cardinalities, as well as the cardinalities of subgroups of its codebook. To end this example, you can see that ALOCO codes result in having a continuous and discrete power spectral density component. The continuous component was calculated via our method, described, and matched the Monte Carlo results perfectly. This discrete component was also calculated using Fourier analysis on the periodic portion of the autocorrelation function. More on this is provided in our longer talk as well as our paper. Formalizing the patterns seen in ALOCO OSTMs into a general result was a bit of an art. But what it boils down to is that these entries were dependent on the code parameters and codebook cardinalities as mentioned. So you can simply look at how to calculate these entries as a set of instructions, and these instructions are provided here. Again, our method resulted in power spectral densities that perfectly matched Monte Carlo results. We followed a similar method for generalizing the results of LOCO codes in our full paper, though it should be noted that LOCO codes end up being a 3-level signal due to their bridging patterns, which are just how you add bits in between code words so that forbidden patterns don't occur on transition from code word to code word. And so we end up using our method on a subsignal of the LOCO code and then combining the power spectral density of subsignals into a full power spectral density calculation for LOCO codes. In conclusion, we first provide a method for calculating the power spectral density of any binary level-based code that can be modeled as an FSTD. We also provide a method for deriving the finite state transition diagram of any binary code whose constraint only requires considering a specific number of previous symbols. This provides a bound on the OSTM seen here, very similar to the ALOCO bound that we described in the paper. Additionally, we found that our results match perfectly. With that, I'd like to thank you for joining me for this talk. And please find our contact information below if you would desire to reach out to us. Thank you. Bye.